Our first speaker is from Logix. Cheng Wang is a senior VP for software engineering and a co-founder of the company. He'll be joined towards the end of the session by his presentation with Jeff Tate, the CEO of Logix. Cheng has presented on his architecture before. He'll be speaking to us about the InferX processor. He previously worked in VLSI design for Zoran and is a well-known expert on AI inference. So welcome, Cheng.
Thanks, Mike, and then Mike and Linley for having us. And good morning. I'm very excited to be here. I'm very excited to share with you some very exciting news this morning, actually, about our InferX X1, our Edge AI Inference Accelerator. Now, the chip has only been back for a month, and it's already up and running. It's running very well. We are in the process of bringing up numerous models, including YOLO V3, which we look forward to demo to you very soon in the coming weeks. Let me see if I can advance the slide here. So yeah, today we're officially launching our InferX X1 AI Accelerator, but there's just too much topic to cover in one talk. So we'll actually split it across 2 weeks. Today, we will talk about mostly our InferX X1 silicon. And next week, I think Wednesday, October 28th, we'll be talking about our X1 board, which is our PCIe Express card, and our InferX compiler and software suite. So we built this InferX X1 silicon with one goal in mind, which is to give you the most throughput for the least amount of cost. Cost in millimeter squares of area and cost in power as well. And it's not just throughput, in an arbitrary sense, but it's, of TOPS, but it's actually throughput on the customer model using batch size of 1, because we're in the edge inference case, to get the lowest latency possible. And in fact, the InferX X1 outperforms the Xavier NX on every customer model that we have tried so far, including YOLO V3. Well, YOLO V3 is an open benchmark, but a lot of customers are using that as is. And we also get high accuracy. We're not trading off accuracy or numerical precisions for throughput. We are using the full precision bflow 16 or integer 8 or integer 16. And unlike a lot of edge AI inference chips in similar cost and power category, we have optimized a model for this silicon for large models and megapixel images that the customer actually want to run. Not the 224 by 224 mobile net, but actually say, 2 megapixel YOLO and, high resolution medical imaging, and models of that sort. And as you will see later in the slide, we are quite unique in being able to offer this level of throughput, latency on large models and large images, yet in a small form factor and very little power consumption compared to, especially the competitors with similar throughput. Okay, and actually this chip is just 54 millimeters square, about 7 millimeter by 8 millimeter on the side, and it's in TSMC 16 nanometer non-expensive process, and has worst case TDP, which is total device power in the worst case, worst models, for about 7 to 13 watts. Obviously, your common usage is going to have lower power than that, but when you're designing silicon and board and systems, you care about TDP, so that's what we quote you. And most of this chip is our reconfigurable tensor processor, which we've previously talked about before as NMAX. And the rest of the chip is actually very, very simple. There's a NOC that goes through a PCIe Express Gen 3 or Gen 4, just 4 lanes of them. We've brought up both generations. They work great. And there's a single 32-bit LPDDR for 4X DRAM. And the rest of the chip is basically, scratch pads and simple peripheral things. But really, this is not a very big or expensive silicon, and because we want to result in a compact package, right? We sell chip and boards, but today we're mostly focused on chips. And we're working with numerous customers, right? With numerous applications, robotics, medical image, industrial automation, various cameras applications, autonomous vehicles, just to name a few. And basically 99% point whatever percent of them are using NVIDIA, mostly using the Xavier NX, and those on the higher end use a Tesla T4, and the few on the lower end use a Jetson TX2. So we'll try to show how the X1 compares to all of them. First, we'll compare to the middle of the line Xavier NX, and compared to that, X1 is about 1/7 the die size, with only 1/4 the amount of DRAM. They're in similar process nodes, though TSMC 12 offers some smaller standard cells. But you know, these two chips are not in the same category, but if you look at the benchmarks, for example, and YOLO V3, like I said, is a customer application. We compared to what the Xavier NX can do is basically faster on all of them. On YOLO V3, even with a model that's optimized by NVIDIA TensorRT themselves, we're about 30% faster. And on some of the customer models, we can be anywhere from 50% to up to 11x in this case. This 11x is mostly because we are implementing some of the special convolution operators more efficiently in our scenario. That's really what we think is differentiating us. And you will see later on what kind of stuff that can do for you as a customer that can be evolving your model. Now, to be fair, Xavier, it's an SoC, right? So not all of this die you see here is being used for inferencing all the time. So we can choose to look at something else that's a pure inference accelerator, like the Tesla T4. Now, this is even bigger, right? Both of these are meant to be close processors that can connect to a Xeon or a AMD server. Now, T4 is 11 times the size of the X1, and it's 8 times the number of DRAMs, something like 10 times the DRAM bandwidth because they're GDDR6 or whatever, and we're LPDDR4X. So you will expect the T4 to be, an order of magnitude faster than the X1 based on, these specs. But really, the reality is much closer than you think. For a model like YOLO V3 that's been optimized by NVIDIA, we're about 1/3 of their performance, not 1/10, but 1/3. But then on some of the customer models, you see we can be anywhere from half to even 2x faster than the Tesla T4. Again, I think this can be related to our handling of special operators. But in the end of the day, the message is the same. You can have something that is 10 times bigger with something like 16 times the tops. They're like 130 tops and we're 7.5 tops. Yet the performance is really not as different as you think it will be. So really, tops do not matter. Do not choose an accelerator or any silicon based on raw tops alone. You really have to look at throughput based on the customer's model. How many inferences can you get per second? Yeah. So because this is a little bit confusing to compare apples and oranges with different sizes, you can maybe try to see this a little bit more clearly by normalizing throughput per millimeter squared, which is basically how much throughput can you get for a certain amount of cost, right? Both in DRAM cost and also area, also packaging. So, if you normalize the numbers, the result becomes much, much clearer. We're anywhere from 3 to 18 times superior to these GPU solutions offering today. And that's not because of magic. We're not cutting any corners. You will see it's all as a result of the InferX architecture. It is just that much more efficient than GPUs. So let's go ahead and take a better look at how we can achieve this level of efficiency in our performance. Yeah, but first, let's just be clear, right? I've said this before. We're not achieving this level of throughput by giving up accuracy, by giving up precision of the numerical computations. In fact, we've optimized for accuracy on every dimension, starting with the models we choose to support, right? YOLO V3 is one of the best object recognition algorithms out there, but it has 62 megabytes of weights, even if you're running integer 8 mode. That's a big model. So a lot of the lower power chip cannot run them. For example, the NVIDIA lower end Jetson TX2 cannot run YOLO V3 at any resolution, but we can. And also we've optimized it for larger images, right? We can run YOLO up to 1440 by 1440. That's 2 megapixels, right? And also for higher accuracy in the numerical precision, right? In BF16 and integer 16 or integer 8. And even if we do accelerations like Winograd, right, we have our hardware support, with internal 12-bit precision expanded from int 8. So we're not losing any precision even in Winograd mode. So we can perfectly reconstruct the output compared to non-Winograd accelerator models. So really the 2.25x acceleration comes at no cost to the customer and pure benefit. And finally, we've said this many times, and we'll say it again, do not modify the customer's models. Customers have spent a lot of time, training their design, tuning their model. We do not try to round down any weights to force any amount of sparsity or to zero out any of the weights or activations, unless they're actually zeros, obviously. So really, do not touch the customer model. Customers want no pruning at all. Okay. So now let's look into a little bit of the guts of it now that we've laid out the ground rules. So we have 1D TPU as a core block, and our silicon has 64 of these 1D TPUs laid out in 4 tiles of 16 each. And for these 1D TPUs, basically takes, in this case, 64 cycles to shift in the data. And then once it's shifted in, it gets loaded into a computational block, which takes 64 cycles to do a matrix multiplication. And when that is done, it goes to a third pipeline stage, which takes 64 cycles to unload the output tensor. Now we choose this intentionally as a preference over 2D TPU or 2D-like matrix multiplication strategies because of the flexibility it gives us. As you will see, we have a lot of reconfigurability in our computation, and this 1D TPU or multiple 1D TPUs give us a lot of flexibility in how we want to implement certain convolutions and operations. We can choose to operate on 1D fully connected layers or 2D convolutions or even 3D or higher dimensions by simply connecting multiple of these units in different ways. Yeah, let's go to the next slide. So our 64 tensor processors, these 1D TPUs, are organized into 4 tiles of 16 each. All of these computational units, different levels of memory units, and this reconfigurable fabric all connect through the XFlex interconnect fabric. And these TPUs can talk with each other as well as with the TPUs in different tiles or with the logic blocks in different tiles, all with full bandwidth, with no contention and deterministic latency. Now, this is one of our secret sauces because unlike a NOC-based or similar architectures, this behaves much, much more like a hardware connection once it's configured. It's just that you can arbitrarily configure it via the compiler. Okay. Our SRAM is intermingled with our computation. The L0 SRAMs are inside the TPUs. They're the weights that's currently being worked on. The L1 SRAMs hold the next layers of weights. The L2 RAMs hold the activations. The L3 RAMs all the way out in the SoC is used to hold some of the configuration bits for the next layers. And basically, these levels mostly refer to how far is the memory from the computation. This is not like caching in the traditional CPU sense. And in terms of actual operation of these 1D TPUs with respect to memory access, now this is a very, very simplified diagram showing you just 4 TPUs. Obviously, in our actual silicon, we have 64 TPUs. But say, we are running layer 0 of YOLO, right? There is going to be a set of memories there that is feeding input tensors into the 1D TPUs. In this case, 4 in parallel. And then the output is going to be loaded into another set of L2 SRAMs. And this thing will be reconfigurable in 4 microseconds. And in 4 microseconds, it can then go ahead and shift to the next layer at the end of the previous layer. Now, 4 microseconds may look like some time, but really you have to keep in mind that YOLO has 300 billion MAC operations spreading across 100 layers. So on average, we are going to be executing a layer on the order of milliseconds. So 4 microseconds is a small percentage of your execution time. It's a fraction of 1%. So, but it's very important because once it's reconfigured, you see these 1D TPUs can then be chained in a completely different way for the next layer. In this case, the parallelism is reduced to 16 because we're chaining up 3 TPUs in series. So it comes from L2, chains through here, and then go to another set of L2. This reconfiguration allows us to really switch over the design completely in between layers. And then in cases that the layers have large activations, what we do is we actually fuse the operation. So we can avoid writing out these large intermediate band activations to minimize our DRAM bandwidth. So in this case, you see that, say, the output of YOLO layer 0 has 64 megabytes of activations. We can't fit that on our chip. Most people can fit it on theirs. So the alternative is to write it out to DRAM, or we try to avoid writing it out altogether. And that's what we do. We take the activations from the L2 SRAM, flowing them through the first set of 1D TPUs, activate them, and then flow them right through the next set of 1D TPUs to execute the next layer. And then the output of the next layer gets written into memory, let it be L2 SRAM or L3 SRAM. So really, this fusion allows to remove a huge amount of DRAM bandwidth that a lot of competing architectures may not be able to do. And we have customer models that actually need to fuse even more layers. So then in those cases, this gets you even a greater advantage. And we do need DRAM access to, for example, load the weights and the configurations, but we really try to hide them in the background whenever possible. So while, say, layer 1 is executing in the foreground, the weights and activations are being prefetched from the background. So when the computation has finished for the layer, 4 microseconds, the weights for the background gets preloaded to the foreground, and off it goes running again. And in the meanwhile, the background operation is preloading the next set of configuration and weights. And by hiding this DRAM bandwidth, really, even for a model like YOLO, we're stalling about 4% of the time waiting for DRAM traffic. For single LPDDR4 with just 32-bit interface instead of 512 like some of the competing solutions, this is extremely impressive, guys. We have really hidden a lot of the traffic, even with just very little amount of available DRAM. Now, our last architectural advantage I like to talk about is really our reconfigurability. Everything that I talk about here is only possible because of our reconfigurable solution, but especially here, because everybody can choose to optimize for YOLO or for ResNet at design time. The YOLO's been out for 2 years. But really, when we work with customers, we realize they're modifying these operators left and right all day long. Depthwise convolution is actually a standard example I'm showing you. This is used in like MobileNet, right? But our customers have other form of convolutions and matrix multiplication strategies that are not, considered normal or benchmarkable, right? And those are the cases where traditional architecture really suffers because they've designed to do certain operators very well. But we have a collection of 1D TPUs fully reconfigurable by the compiler. So we can really modify our compiler to support a much, much wider range of operators. And really, for a lot of our huge advantages over, say, Xavier, it's, I think, really caused by our support for these more esoteric layers that just bog down the traditional architecture. And every customer is going to have their own layers that are unique or different, right? Okay, for the last few minutes, I'll talk about some of our timeline and availabilities and pricing. So X1 is working now, but obviously full chip characterization takes some time. We're working with customers right now. They have shared their models with us. And in Q1, we'll be sampling to these new customers. And in Q2, we'll have volume production for parts up to 800 megahertz. And unlike the Xavier, we'll be extending to a wider temperature and operation range, for example, industrial as well as aerospace specs. Our 933 megahertz part will be later in 2021. Now, when it comes to pricing, X1 is much smaller than Xavier and T4, but for the same level of performance, 1,000 unit price is about 1/2 to 1/4 of their 1,000 unit price. So existing Xavier customers can shift over to X1 and enjoy higher performance, lower power, smaller size, and lower pricing. But we don't just want to convert existing customers. There's a huge untapped market, and we want to greatly expand the market. So we're also sharing our price for 1 million units. So we can sell these X1 in very large quantities, so customers can add high performance, high throughput inferencing to systems that simply cannot afford it today. Now, comparing to Xavier, $39 is 1/10 the price. Now, there's a lot of software support that include this pricing as well, and we'll talk about them next week. But basically, in the end of the day, we map TF Lite Onyx frameworks directly. So if you're using them, you can convert over with little to no work. So we've shared a lot of information. So let's summarize. Right? X1 is much smaller than competing solutions from NVIDIA. Our 933 megahertz part is half the price of the Xavier. Yet it's 30% faster on YOLO and up to 11% faster on some of the models. So you can see a huge gap difference in performance here. At 667 megahertz, our performance is essentially the same for YOLO, but we sell for 1/3 the price. And at higher volumes, the pricing is much more aggressive. And even the lower end Jetson TX2 customers can benefit. Their module sells for $249. X1 is cheaper and runs 5 times faster than TX2 at similar power, and TX2 can't even run YOLO. So you get way more throughput, way more performance for something that is substantially cheaper. Okay. So people will ask, I'm almost done here. What about competitors, right? We actually don't see customers using basically anything else other than NVIDIA. But after some digging, we did find another product that runs YOLO that is from a company called Blaze. Their cheapest module sells for $299. And we don't know why they don't publish YOLO at a higher resolution. I'm sure they have a reason, but the only YOLO benchmark they had is 416 by 416, which is medium small resolution at 50 frames per second. Our lowest end X1 can run the same YOLO model faster at comparable power at 1/3 the price. And of course, you can go to a higher performance X1 and still save a lot of money and run even faster. And then more than enough to cover the cost of one additional DRAM that doesn't come with the Flex Logix chip itself. Okay, so we covered a lot this week. We'll cover a lot more software in next week's presentation, but in essence, we'll have general software availability in Q2 next year. But we're bringing up our compiler right now in the next few months, and we're focused mostly on customers that are in production or plan to be in production in 2021, using thousands to millions of units. So if you have those applications right now, please share them with our extremely handsome sales VP, so we can benchmark your models right now, and based on how unique your model is, we can typically give results for you within the next few days. Okay. Thank you. I'll talk to you guys more next week, and I'll take questions now. Mike, you're on mute.
Yeah, how's that?
Yeah, perfect.
Yeah, sorry about that. So we had just a couple minutes for questions. We had one that I thought of myself with the one-dimensional tensor processing. Do you see any disadvantages, for example, in terms of latency or for some applications?
Actually, no. So basically, for applications where it makes more sense to operate these 1D TPUs like a traditional 2D TPU, the multiple units of 1D TPU will basically process the rows in parallel, so it behaves much more like a 2D TPU. So it's basically just an additional degree of freedom by not hardwiring as a 2D TPU that we can reconfigure our fabric to connect the 1D TPU in whatever dimension we prefer.
Okay, then we have a question. How much memory is on the InferX chip?
There's 8 megabytes of L2 for intermediate activations. Greater than that, it has to be written to memory in the SoC, either the 4 megabyte of SRAM or the LPDDR. One module of LPDDR can be 512 megabyte to 1 gigabytes, maybe a little bit bigger.
And then I think you mentioned you support integer, 8, and B float, but question on what data types you support.
Excuse me, on what bin size? I'm sorry.
Data types do you support?
We support int 8, int 16. So int 8 by int 8, int 16 activation by int 8 weights, as well as int 16 by int 16, as well as bflow 16 by bflow 16. Is that the data type that they're asking about?
Right. Could you want to go ahead and stop sharing your screen so we can see your handsome face full screen? There we go.
All right.
There was a question, what were the biggest differences in the customer models and YOLO V3 that gave you that advantage? Could you talk about what some of the special features were?
Yeah, so basically, customer models can diverge from standard benchmarks in a number of ways. For example, one of our customer models have a much greater ratio of computation versus memory access. They need way more memory access and computation. Their computation have, say, 16 channels. If you look at YOLO V3, their computation goes up to 1,024 channels of computation. So you'd be computing a much bigger matrix while just writing a much smaller amount of activation to memory. Those are more optimized models because they use the max more efficiently, but a lot of customers don't need that. So we see customers that have 16 channels of computation sizes, say 3 by 3 by 16, but then they have to write it out for a huge resolution. So they're constantly writing to DRAM. So in those cases, our deep layer fusion worked very well. So we don't write to DRAM until the end of multiple layers of computation have been fused and computed. In other cases, the customer may use different types of convolution. They may be using some kind of, say, 3D convolution or some other convolution where they're convolving not just across space, but also across time. So those are cases where, traditional conv engines, if you didn't design for those kind of stuff, won't be able to handle them very efficiently.
Okay, great. Well, I'm afraid that's all the time we have for now. You'll be in the breakout session later.
Yeah,
and
I'll be there myself.
Also, Cheng will be back next Wednesday for the follow-up of the second session from Logix. So thank you, Cheng.
Yeah,
and
thanks, Mike.